Right. So my talk today will be dedicated to digital design for traction motors. They do not use rare earths or rare earth-free traction machines. The following topics will be briefly covered. So just a quick introduction to electrification challenges, a reminder for all of you to what's going on the stage, then a short introduction to digital design process to understand what are the features that are requiring the approach. And then I'm going to present you three special cases, one for an induction machine, one for synchronous reluctance, and one for a synchronous one-field machine, all three topologies with no permanent magnets or with no rare earth configurations. From the electrification challenges point of view, quick reminder that all of the climate changes, this push for greener technologies, having products with the low emissions of carbon dioxide. And along with this, we are dealing with electrification, e-mobility, trying to replace combustion engine with electrical machines. And here you can see different considerations like potential solutions for this type of machines can be pushed further, running at higher speed, increasing the number of poles, or alternative solution like synchronous reluctance, electrically excited and induction machines with reduced rare earths. Obviously, due to the significant variety, the performance of such machines will tend to have a common standard designed for all the technologies. However, it's difficult to guide the optimal configuration just if we focus on one aspect of the machine design, like electromagnetic only or thermal only, or only this, but neglecting the mechanical or the whole system in its entirety. Along with this, we discuss about dedicated design software, which on top of the fact that it has to evolve, so then all the demands in the new technology development has to be covered, has to be as well user-friendly and easy to use also for the non-specialist users. From the digital design point of view and electrification, if you see here on the left-hand side, if we look at existing engines, either one from a vehicle, automobile combustion engines, or a jet engine, you can see how many parts are in here, complicated assembly, a certain cost. Then we can migrate into electrical machines. The number of components you can see it's much less than the others, just typically 100 parts compared to thousands in the others. But we do need to consider all the multi-physics aspects, magnetic, electrical, thermal, mechanical, noise and vibration, look at the entire system, the battery, the inverter, the gearbox, and the vehicle itself in which the machine the electrical machine is placed. What's the status now? How we can increase the power density, the torque density for electrical machines? Here we can see historically how electrical machines have evolved from industrial motors, an induction machine here, where typically the torque density was around 1 Newton meter per kilogram. Then moving to Remy motor is actually Borg Warner when it was released a few years, maybe 20 years ago, with hairpin configuration, and we had 10 Newton meters per kilogram. In aviation, we have Siemens machine that reach 30 Newton meters per kilogram. And in large machines, wind generators, we can deal with this type of torque density. While from NASA, it's the aerospace organization from United States, and they are typically pushing forward the boundaries for high-end applications. And they target this type of torque density or power density. And on the right-hand side, we can see one of the features that we need to consider when designing powertrain, electrical machines with the entire system with high power density and torque, we need to look at the improving the cooling system. Or otherwise said, we have to increase the heat transfer coefficient. These machines are typically cooled using forced liquid. And therefore, to push it further to higher torque and power density, we have to be able to increase the heat transfer coefficient. And here you can see different considerations, what you can achieve using different cooling techniques. From the e-mobility point of view, traction motors for electrical vehicles, there are different solutions already on the market. Most of them are based on permanent magnet synchronous machines. And you can see here a list of some of the topologies. In few cases, you may find induction machines. The most well-known solutions are certainly either Tesla or Audi e-tron, and as well Mercedes-Benz EQC using double induction machines. Few exceptions on the wound rotor synchronous machine for Renault, and as well it's used in BMW, the latest release of electrical vehicles. But otherwise, you can see it's dominated by PMSM almost everywhere. If we look to these topologies and we build this type of diagram looking at different aspects, recyclability, performance, power at maximum speed, NVH, manufacturing, and here you can see the legend of this image, how they compare one to another. Clearly, from the performance point of view, the rare earth permanent magnet machines are the best from the performance point of view. This is undisputable, as we discussed right now. However, the other solutions may have their own advantages, either in the manufacturing sector. We can see the switch reluctance scores very high in the manufacturing, or the induction machine looks very good from starting. This is why you'll find it in vehicles like Tesla with front axle having an induction machine that will ensure fast starting capabilities of the vehicle. Or here in the other aspects, we can look recyclability, where they score well these solutions with no permanent magnets, with no rare earths, and showing us that the whole picture is complex, and we need to consider all the aspects when we decide to go for rare earths free solution or the solution with permanent magnets. Further, beside the topology of the machine, we need to take into account the vehicle itself. And here you can see a diagram where we have the entire vehicle with the wheels. We have a two-axle solution. We have a machine on the rear axle, one on the front axle. We have inverters for both of these. We have a common battery, the gearboxes, and this can be investigated using a digital design. All these components can be put together, and from a library of existing elements, we can select and check from the system point of view what will be the optimum solution. So as a designer, the digital designer, let's say, one can select PM machines combined with rare earth free or two rare earth free solutions, or two PM solutions together, different gear ratios, different power levels, and obviously discussing as well the battery level as well. And this can be analyzed into a complex and complete package, so then we can find the optimum solution for a given system. How about the digital design aspects strictly related to and more focused on the machine itself? When we design a new solution, we obviously have to look at different innovative solutions. So we are looking at the design, how innovative it is, configuration of this. From the manufacturing point of view, what we can do better to reduce the cost and to improve the performance of the machine. And last but not least, innovative materials. What materials can be brought into the question? So then we improve the performance, either electrical steel, winding materials, cooling system for the materials for the cooling. Obviously, as well, the PM machines, permanent magnet materials, can be considered what materials are innovative and can be used with the lower cost. So designing targets, obviously always looking at higher efficiency, increased torque and power density, reducing costs, increasing volume and mass production, increased integration and shorter development cycles. And typically from the digital design process point of view, we discuss about this type of funnel approach. So you, as a group of engineers, let's say we have electromagnetic engineers, the mechanical, the thermal engineers, the power electronics. So we know from the vehicle point of view what is required. So we have a certain volume, a certain mass, a certain speed of the vehicle has to be achieved, a certain mileage, the range for the electrical vehicle. And then we consider different solutions with or without errors, attempt few initial solutions to reduce the space of the design, and then we can go into detailed design when we can optimize one solution on topology using 2D, 3D finite element, power electronics, modeling, fluid dynamics, everything that can be done through simulation and saving from the cost of manufacturing, so that when we come out with the final solution, will be very close to what the actual performance of the system will be. It's always complex to design electrical machines, considering even one simple parameter. Here, I give you the example of the split ratio, which is the ratio between the inner diameter of the stator, assuming that it's a configuration with outer stator, inner rotor, over the outer diameter of the stator lamination. And you can see the impact. If you increase it, you can get increase in peak power, peak torque. However, the performance in continuous power will be maybe reduced. The torque ripple may increase, and we don't want this. The drive cycle efficiency will increase. On the other hand, the noise and vibration rotor stress will increase. The cost may be slightly reduced, because increasing the diameter, we can reduce the stack length. So there is no black and white or 1 or 0 solutions. Everything that we do, any parameter that we change will have plus and minuses. Not everything is going to improve totally the performance of the machine and or make it worse. So it's always a trade-off, and this is where the digital design process comes into effect and helps us finding the optimum solution, considering all the aspects, so that when a set of solutions is emerging, it's easier to select one or another that will satisfy all the complex criteria that have been put in place. So now I'm going to give you 3 examples of possible solutions with electrical machines, no errors for traction. That these are based on projects where we've been involved in the past. The first 2 examples are coming from a Horizon Europe project, Refri Drive, where we been part of a consortium, and our scope was to develop series of traction machines with no rare earth materials. So the first I'm going to show is the traction induction machine case. Here we see, as a quick reminder from the theory point of view, the torque that this type of machine will generate, a simple equation, trying to understand what can we do to improve this performance. Why are we focusing on the torque? Remember that typically when discussed about electrical machines, we have parameters like power, voltage, current, efficiency. However, as an electrical machine powertrain designer, what we sell is torque. This is what we guarantee. And then depending on the rotational speed that the machine will rotate, we can achieve a certain power. So therefore, it's essential to be able to go to torque level when designing the machine rather than power. So then will give us a better understanding of the machine capabilities. The torque itself for the induction machine clearly will depend on the volume, which is D squared L. On the magnetic loading, this B1, and the electrical loading. So it depends on the current, winding, volume, materials, and this is in a short way put. These are the main elements that will help us getting higher torque from an induction machine. They are very well known. Technology, induction machines have been developed for more than 100 years. And even though they cannot match the performance of the PM machines, still because it is well established, the manufacturing has a lot of advantages. It's simple to make it, robust, cost effective, and last but not least is fault tolerant. It's one of the most forgiving electrical machines in performance. Cannot be demagnetized, take over even a lot of heat, thermal stress, mechanical stress. If anything will fail in an induction machine, typically in vast majority of cases will be at the bearings level. Through digital design, we can achieve significant improvement, so then they can compete, maybe not the same level from the efficiency point of view, that certainly they can deliver the same torque and power comparing with an equivalent permanent magnet machine. And here you can see the link where you can find what I'm going to describe about the induction machine. This was developed, the example that I'm going to show is developed, I mentioned, during this REFRIDAI project, where the target was to design electrical machines for traction application with no rare earths. From the induction machine point of view, we settle on a solution with a copper rotor to have high speed capability, low cost manufacturing. The cage can be die-casted or fabricated, hairpin winding technology, low cost, lost materials, and obviously multi-physics optimization, considering all the elements at the same time, electromagnetic, thermal, mechanical, and looking as well to the power electronics. Some key figures. We had as reference Tesla S60S, for which we had the specific power, specific torque, and peak efficiency, and the target was to better or to match these requirements. How we did it, the design for the induction machine, I mentioned, was considered from all the aspects point of view, magnetic, thermal, mechanical, looking at the volume, taking into account the limitation coming from the battery and the power electronic system, the current waveform. And for the rapidity of the optimization, we made use of an equivalent circuit, which is classically, you recognize it here. This can be transformed into L or gamma, inverse gamma. But any element in this diagram is actually nonlinear. So the procedure was to pre-calculate using advanced systems of calculation, finite element based, where all these elements were nonlinear. So we had the lookup table for the magnetizing inductance, core loss equivalent resistance, the two leakage inductances stated or a rotor resistance, and last but not least as well, the variation of the stator resistance. Having in mind that at high speed, both R1 and R2 will suffer from skin effect, so will be variable with frequency. Obviously, more is the case for the rotor resistance, but as well the stator resistance, having in mind that this was manufactured using hairpin winding. For optimization of the design, considering the standard WLTP cycle, we created clusters of points into this drive cycle, and this is a more efficient way to optimize the machine to get the best average efficiency, considering only these 5 clusters rather than all the points in one go. So it was a method to speed up the multiphysics optimization. The topology, you'll find it's already published in literature in several articles, including the one that I'm quoting right now. It's a 4-pole 36-slot machine with 50 rotor bars, just as an indication of the stator outer diameter. Materials, relatively standard, 0.35 millimeter thickness M235. And the material for the cage was either copper silver alloy or copper ETP for die-casted solution. Some information about the turns per phase. There were 4 layers in the winding per slot. Do a good slot fill factor reported there. From the mechanical point of view, this machine was designed to run to over speeds up to 24,000 RPM. With a maximum rated value of up to 20,000 RPM. And you notice the rotor bars are closed, and the mechanical stress analysis show that they can withstand easily any the effect of the centrifugal force on the rotor lamination, including the effect of the end ring of the rotor bars as well. At a very high speed here is reported at 22,000 RPM. Another aspect that we had to consider into this multiphysics design was the impact of the non-sinusoidal currents. And you can see how they look like. In 2 cases, one for operation at 6,000 RPM, 370 Newton meters, with a fundamental of approximately 205 Hertz, and the PWM carrier was at 20 kilohertz. The same PWM carrier frequency was used in the other point, where it's the maximum rotational speed, lower current, but the current waveform is as well more distorted. You can see as well the harmonic spectrum reported, comparing the current waveform harmonic spectrum overlapped with the PWM carrier order. With this type of waveforms, during the optimization, it's possible to calculate performance of the machine. And here we are looking to one aspect, meaning that inside the stator, I mentioned that the winding for this machine is a hairpin with 4 winding layers or 4 conductors per slot. And you can see the ohmic losses, how they develop. This map is including both the DC and AC loss components inside the winding. And you notice the lower conductor, the conductor placed over the slot opening, they all are suffering higher from a higher thermal stress point of view, because the losses will be higher. And here on the right hand side, we have a diagram showing by how much the how much will represent from the ohmic losses, how much it's DC copper loss, which is the amplitude colored in blue, and in red we have losses due to the AC effect. And for a better comparison, we have the case on the left hand side in this slide, where we have efficiency map of this machine with sinusoidal current, which goes closely to 96%, but very little, very small region. This is in sinusoidal. But once we consider the PWM effect, you see it's a drop in maximum efficiency, about 1 point. Maximum we can achieve is 95% efficiency. Obviously, the peak torque and is the same in both cases, 370 Newton meters. But the average efficiency has been changed because of the effect of the harmonics within the current waveform. In the same design, we investigated two possible cooling solutions. The one on top, it's very similar to what it's in induction machine e-tron, as well, maybe a bit similar to Tesla, meaning that ethylene water glycol fluid was circulated through the rotor cooling, and then from the rotor through a pipe, it was circulating inside the stator water jacket, and then from there, the same liquid was going to the inverter. So the same fluid was used to cool both the machine and the associated inverter. And the other solution, it's a combination between water jacket with ethylene water glycol and oil spray, where the oil will circulate through the shaft and with nozzles to spray out over the end winding. And with this configuration, if you look to continuous power, what is? Continuous power is what we consider the machine performance that it's achievable without exceeding a certain temperature limit. For an induction machine, obviously, the two elements, or three actually, but the main two elements that we consider from the thermal point of view and are critical from this point of view is the insulation of the stator winding. In this case was insulation class 180 degrees Celsius or H. And for the rotor bars, we assume the same maximum temperature 180 degrees Celsius. Additionally, in induction machine, I mentioned earlier, bearings are critical from the potential fault point of view, and the temperature of the bearings as well had to be maintained below 120 degrees Celsius. So with these three components in place, together with electromagnetic, considering as well the mechanical noise and vibration, from the thermal point of view, we can compare the two cooling systems. The continuous line is the one with water jacket for the stator and the cooling through the rotor, using only one liquid, the ethylene water glycol, and the other one is a combination between two cooling systems, one for the stator water jacket and the oil spray liquid coming from the rotor through nozzles and spraying over the stator end winding. And we notice that we have some benefits. For the first system, we can achieve higher peak torque in continuous performance at lower speed, but the other one with oil spray is more relevant, especially from the higher rotational speed range point of view, when we can achieve higher power with the oil spray system. Another machine that I would like to briefly present you is the synchronous reluctance machine. The torque equation displayed here, you notice already known, this torque is proportional to the saliency ratio and the current, and not directly depending on the rotor field. The rotor field doesn't exist. Synchronous reluctance has no excitation. So the calculation, based on the calculation equation for the torque, we can see that the ways to increase the output of this machine is either more current, IDIQ, or higher saliency ratio, or the difference between these two DQ axis components of the magnetic structure. This machine is by far the simplest to build, robust, fault tolerant, very cost effective. However, the efficiency is lower than the other cases, and the power factor is quite low compared not only to PM but even to IM, to induction machine. You'll end up, therefore, you end up with higher costs for the battery and the inverter. So what we save on the machine may be spent extra in the power electronics part. However, we can achieve improvements in the design of such machines using digital design technique. So what we did for this case, considering three possible solutions, all with 4 flux barriers. You can see 4-pole 36 slots, 6-pole 54, 8, and 72. And considering 4 points one at peak torque, one maximum power, maximum speed, maximum efficiency point, and low torque and low speed for the working region. And here we have some dimensions of the machine and the electromagnetic performance that was required. Through optimization, this is what has been achieved from the rotor point of view. In the synchronous reluctance machine, the most important thing was to optimize and get the best design for the rotor lamination. That will not only maximize the saliency, LD and LQ difference, but as well to be well robust and rigid from the mechanical point of view. And the 6-pole was selected from the 3 combinations. From what you see here, this column highlighted in red. And going further from initial optimized design using standard template topologies, then one of the new avenues to investigate the improvements of performance for not only synchronous reluctance, but as well for interior permanent magnet machines, for any machines with where the rotor structure has to be carefully designed to improve the magnetic, but as well to retain the strength from the mechanical point of view. So it's the technique called topology optimization. And from the left to right, you see what has been achieved by topology optimization technique. Obviously still 4 flux barriers, but the ribs have been placed differently. And critical maximum mechanical stress has been moved from different sections. Here was on the left hand side, these arrow points where was the maximum mechanical stress, what is moved in this region when you do topology optimization. And the workflow for optimization of the synchronous reluctance machine is given here. You start from a preliminary design, you optimize it magnetically, then using topology optimization, you can get a proper dimensions, the placement of the flux barriers and the relevant ribs. Then you can go into parametric model, selecting the parameters that you want to change once you selected some useful candidate design from topology optimization. And last, we get into magneto-structural optimization. And here we have a comparison between 3 possible solutions for the same machine, where you have no radial ribs, all good, but mechanically will be difficult to maintain this. But from the saliency ratio, which essentially means that I can get more torque, no radial ribs will be the best, but it's an ideal case. Then with ribs, this is the what's happening with the black line. And then in the middle through optimization, so we reached a compromise using the topology optimization to improve what was originally obtained. We couldn't match, obviously, the case with no radial ribs, but still was a good improvement using the topology optimization. If you look to the peak torque and peak power, again, the ideal case with no radial ribs was the best, but mechanically pretty much had no viability. Again, using the topology optimization was improved both the torque and the power capabilities. On the power, you notice this known aspect of the power spectrum for the synchronous reluctance machine. The peak performance cannot be sustained. In this case, we are looking at 200 kilowatts peak performance for a long speed range. So they always lack this capability of sustaining quasi-constant power for a wide speed range. Now, from the performance point of view, you can see the calculated efficiency map on the left. And on the right, when prototyping was decided to be approached, was a scaled down efficiency map for a machine that is smaller. This on the left-hand side, you have the design for a machine that's supposed to deliver 200 kilowatts output power, while this one was only for 75 kilowatts output power. Was experimentally validated and looking good with a peak performance around 94% efficiency, the scale down topology optimization solution. And last case as well, rare as free, is the one-field synchronous machine, which it's seeing quite a bit of a revival. Even though it's more complex to build, it does have obviously the advantage that is not using permanent magnet materials, rare earth materials, and it can be used successfully to achieve high efficiency, high torque, and operating at the constant power level. The torque equation shows us that beside the reluctance component, torque component that we've seen already in the previous case for the synchronous reluctance machine, we have the advantage of adding the alignment torque component, which depends on the rotor field and the current. So then essentially behaves like a permanent magnet machine. We have both torque components, and we can consider different aspects to improve the performance of this machine. It's more efficient than both induction machine and synchronous, and torque density is the same. So if you want, it's an intermediate stage between induction and synchronous reluctance all the way to PM. However, it's more complex to build. The higher inverter cost is both the armature and the rotor excitation, they need to be energized. They have less fault tolerant capabilities. The more components you have, obviously you introduce another degree of uncertainty and possible failure in the whole system. We can improve this type of machine, obviously, using digital design approach. And here, as an example, we are showing you an exercise that we did, trying to take two existing PM solutions, IPM solutions on the market. One was the IPM used in Tesla 3, which is a 54-slot 6-pole configuration. And the idea was to retain the same cooling system for the stator, the same stator lamination. Obviously, you can change the winding number of turns per coil and the pattern, and swap the rotor from the IPM with the synchronous one-field topology. Additionally, we included a cooling rotor shaft through using rotor shaft spiral groove cooling. So the water ethylene glycol cooling liquid that was used for stator being used as well in the rotor. And this is what we managed to achieve through optimization. The target was easier because the stator is already fixed. We had only to vary the number of turns per coil for the stator. You notice these channels that are on the stator lamination through which the liquid is circulated to cool this assembly, the stator assembly. And through optimization, we verified what solution can be achieved. You get a sort of Pareto frontier here where you can identify the optimum solution. In this case, we were interested to get the maximum torque at 40 Newton meters. Obviously, beside maximizing the torque, we had to try to maximize the efficiency and to maximize the von Mises stress in the rotor lamination should be below the yield stress from the mechanical point of view. Some results that were obtained using this type of modeling. There were few considerations to be given from the mechanical point of view at these corners for the rotor lamination, while from the thermal point of view, through digital design, it's possible to investigate the case when you control using maximum efficiency control strategy for this type of machine to retain the capability performance of this machine, while at low speed, the maximum temperature 180 degrees for the stator was here the limit, while the green, this is the temperature for the rotor. the rotor winding temperature is the limiting factor at higher rotational speed. And here comparing the two solutions, the Tesla IPM, which is the blue curve, versus the brown curve, which is the wound field synchronous machine solution. They achieve roughly the same peak torque with an advancement, a bit more peak power obtained by the IPM. You can see here we couldn't match the same performance within the same dimensions, having exactly the same stack length, the same stator lamination. But this was more or less expected, because we cannot better the PM performance within the same volume. While on the torque point of view, we achieved slightly better torque for the wound field, just few 450 Newton meters versus 437 for the Tesla solution. Very important here, you notice on the x-axis you have the load angle, or the torque angle, or the phase advance. There are different definitions, which is the angle measured from the q-axis. And if it's zero, means the current is aligned with the q-axis, with the back EMF axis. If it's plus, it's advanced, and if it's minus angle, negative angle, this means that it's retarded. And it shows that indeed the maximum torque was achieved for the wound field synchronous machine with slightly negative phase advance. The reason being that for this type of machine, the d-axis inductance can be higher than the q-axis inductance compared to the IPM. So while the IPM was had the optimum phase advance somewhere around 40 electrical degrees, for the wound field we had slightly just below 0 phase advance. The same exercise was done comparing the Chevy board, which is another IPM machine with 72 slots, 8 pole with 6. This one is using hairpin winding with 6 layers per slot. So the same stator was maintained in both solutions, just replacing the rotor with permanent magnets with the solution with the wound field salient pole configuration. And the same considerations have been given: optimal rotor geometry, maximizing the average torque, the weight, the efficiency. Pareto front reported here, picking as optimum solution the one that was giving us minimum losses, while considering as well the maximum torque that can be achieved. And comparing the two solutions, again, the same aspect can be observed. At power level, with compared to Chevy bolt, we are almost identical with the wound field synchronous machine. While on the peak torque, also very little difference between the two, just the same aspect that the optimum phase advance, it's in this case actually was slightly positive compared to the previous design. And as expected for the IPM, the optimum phase advance, it's somewhere close to 50 electrical degrees. Conclusions: rare earth solutions, they do represent obviously a viable solution for electrification. Good performance, cost, it's always good to mention that they typically can be slightly cheaper than rare earth solution. Sustainable production, and with digital design it's possible to squeeze the last drop, if you want, to try to improve as much as possible, looking to all multi-physics aspects to improve the design of such technologies. The actual and future trends designed for this type of machines, looking into the spectrum that exists on the market, is clearly hairpin winding. This is known for essentially because it's ensuring that the overall copper losses will be lower. And the technology is there to allow optimization easy implementation. You can have several number of layers of in the slot, and they go hand in hand, this hairpin winding, with liquid cooling or oil spray in order to be able to remove the heat from the winding. Additional special electrical steel, it's always important to be able to be used. So even though the cost will be slightly higher, the benefits from the improvement that can be achieved using electrical steel, reducing the dimensions of the machine will be important. We can look at the copper alloys at additive manufacturing, trying to get through 3D printing or 3D technologies, different solutions for this type of machines. And this is an acknowledgement to our colleagues from University of L'Aquila and my colleagues from ANSYS MDR. Thank you for your attention.